In this video, we're going to be talking about independent and dependent probabilities. And so we're going to have events that follow one another, and they're either going to affect one another or they're not going to affect one another. First, let's talk about the independent events. Those are events that do not affect one another. For example, we could have a jar of marbles of all different colors. If I choose a marble, it doesn't matter what color, and then I put that marble back, and then I choose a second marble, well, the probability of choosing any colored marble on that second attempt is not affected by whatever color I chose on the first one because I put the marble back. So because I'm resetting my sample size each time I put the marble back, these events do not affect one another, so they would have independent probabilities. Sometimes events are not so easy to determine whether or not they're independent. And so what we're going to do is we're actually going to use this equation here, giving us the probability of independent events. And we're just going to check to see if it's true. If the probability of one event times the probability of our second event is equal to the probability of the intersection of those two events, then that is what we consider to be independent. And so if this equation is true, then we have independent events. If we don't get this equation to be true, we will not have independent events. So that's going to be our first couple of examples here. Here in this data table, we got some domestic flights and international flights that are arriving late or on time. And so maybe at first glance, it's kind of hard to tell whether or not these events would be independent of one another. So what we're going to do is we're going to say that event A is the event that a flight arrives late, and we're going to call event B when a flight is international. So let's find the probability of those two events, and then we'll find the intersection, and we'll see if the product of those two probabilities is equal to the intersection. First, let's find a probability of event A. Excuse me. The event that a flight arrives late is given in this column. We got 15 out of 150, sorry. And then the probability of a flight being international. Here's our international row, so we got 50 out of 150. So if I multiply those two probabilities, it's going to be equal to the intersection. Let's find the intersection here. What's the probability of an international and late flight? So here's our international and late flight intersecting here at 5, so 5 out of 150. So we'll just simplify the left side here and see if it's equal to the right side. So 15 times 50 is 750, and 150 times 150 is 22,500. We could reduce these. In case you didn't know, the greatest common factor between those two is 150. And so if we divide top and bottom by 150, we do in fact get 5 over 150. So the product of those two individual probabilities was equal to the intersection of those two events. So those events are in fact independent. Certainly didn't seem like it at first glance, but we can prove it using the math here. One more time, we got a data table here with a couple of things that may not seem to be independent at first, and maybe they're not independent. Let's do a check. We got 200 randomly selected apartments in a city. We got some single occupants and multiple occupants, meaning we got one person living in them or more than one person living in them. And those apartments either have one bedroom or two or more bedrooms. All right, so is the event that an apartment has a single occupant independent of the event that an apartment has one bedroom? Well, I don't know. Let's see. Probability of event A we'll call the single occupant probability. So let's see how many single occupants we have. We got 82 out of 200. We'll call event B an apartment that has one bedroom. So let's see how many one bedrooms we have. We got 70 out of 200. So there's the probability of choosing that. Let's find the intersection. So that would be an apartment that has one bedroom and has a single occupant. So single occupant and one bedroom intersect right here at 68. So 68 out of 200 would be the probability of the intersection. So is the product of these two independent events, or sorry, individual events, equal to the probability of the intersection? That would see or make sure that they're independent. 82 times 70 is 5,740, and 200 times 200 is 40,000. I can reduce by a bunch of different numbers, but dividing by 20 would be the greatest common factor. And so the most I can reduce this fraction down to is 287 out of 2,000, and that is not going to equal 68 over 200 no matter how hard I try. So these events are not independent of one another. And so there we have our check to see if events are independent of one another, just guaranteeing that this equation satisfies or holds true. And if it does, those events are independent. If it doesn't, they're not independent. The reason why we need to check is because if we know they're independent, well, then we can use this formula to solve for our probability of the independent events. Although if it's obvious enough that they're independent, then you don't necessarily have to do the check. That's just there in case you're not quite sure. So this time, let's go back to the marbles that we knew had independent events, and let's just practice finding the probability. So we're going to continue to use this equation. If events are independent, we're going to multiply the probability of each individual event. And then we will get the probability of one happening one after the other. So this time, we got the same marbles in our jar here. We got 14 red, 17 yellow, 13 blue, and 11 green. So the total number of marbles is going to be 55. We're going to take a marble out of the jar, and then we're going to put it back. So each time, we're going to have 55 marbles in our jar. Then we're going to take a second marble, and so we're going to have two events, one after the other. We know we're going to multiply those two events. Let's see what the individual probabilities are. If we select a yellow marble first, well, that would be 17 out of 55 marbles. And then we select a green marble. Well, there are 11 green marbles out of 55. So we have our two probabilities, 17 over 55 times 11 over 55. You could multiply the tops and then multiply the bottoms and then reduce, although that would make the reduction a little bit harder. Let's reduce first. That always makes it a little easier. We know that 11 and 55 could be reduced to 1 and 5. So 17 times 1 is 17, and 5 times 55 is 275. Because we reduced before, we don't have to reduce now. We are in a final reduced form. Although the fraction form maybe doesn't make the most sense, I like to think about it as a percentage. So that would be approximately 6% probability that we select a yellow marble and then a green marble. Next, let's take a look at a spinner. This spinner has got equal area portions here, so the probability of landing on either section is equal. And it doesn't matter how many times I spin it, my probability is always going to be the same. There are 8 sections, and so I'm always going to be out of 8. So again, we got independent events. Doesn't matter how many times I spin it, it's not going to affect the next spin. So what's the probability that you spin an even number? Well, let's see how many even numbers we have. It's a little washed out. This is a 1 here, and this is a 6 there. So we got 1, 2, 5, 6, 7, 8, 10, and 12. So the number of even numbers we have 2, 6, 8, 10, and 12. There are 5 even numbers. So the probability of spinning an even number would be 5 out of 8. Next, if we spin an odd number, we have 1, 5, and 7, so 3 odd numbers there. So 3 out of 8 would be the probability of landing on an odd number. So what's the probability that we spin an even number and then an odd number? Let's multiply our two probabilities and do 5 times 3 on top, that's 15. 8 times 8 on the bottom is 64. We couldn't cross-reduce anything here, so we can't reduce our final fraction either. And then we could, although think about it in probability or percentage form, 23%. So 23% chance of spinning an even number followed by an odd number. So those are independent events. We just multiply the probability of each independent event. What happens if we have dependent events? Those are going to be events that do affect one another. We're going to have a slightly different equation, but we're still going to be multiplying the probability of our events here. It's a little washed out. This is supposed to be a B here and a B over here. So as we read it, the probability of the intersection of our events, A and B, is equal to the probability of event A times the conditional probability. So if you haven't seen conditional probabilities before, you should check out that video or lesson first so that you understand this notation and understand what I mean when I say conditional probability. But really, it's the probability that B is given or occurs, the probability of getting an event B since A occurred. So they're piggybacking events. Given that A occurred, what's the probability that B will occur? That's a better way of saying it. All right, so a little bit complicated here, but really the math is the same as what we just did, just multiplying two fractions. Let's see if we can set up those individual probabilities and see why we have dependent events this time instead of independent events. In this example, we got 6 tiles. We got the letters A, B, C, D, E, and G. We're going to choose a tile, and then we're going to put it aside. We're not going to put it back. So because we don't put it back, that's going to affect the probability of the second tile that we choose. So find the probability that we choose a vowel first and then a consonant. So let's find the probability that we choose a vowel. So out of 6 tiles, there are A and E, 2 vowels. So 2 out of 6 we could reduce down to 1/3. Here's our conditional probability. So given that we chose a vowel or chose a tile to begin with, what is the probability that we choose a consonant next? Well, first of all, since we chose a tile and did not put it back, now we only have 5 tiles in the bag. So our probability is going to be out of 5. Out of those 5 tiles, how many are consonants? That's that conditional part. Well, we chose a vowel first, so we still have the same number of consonants. We still have 4 consonants left. So 4 out of the 5 tiles left are consonants. There's that conditional probability. Let's multiply our 2 individual probabilities here. 1/3 times 4/5. We get 4 on top and 15 on the bottom. So 4 out of 15, or approximately 27% chance of choosing a vowel followed by a consonant. Let's do another one, a similar one. This time we're going to choose a consonant first and then another consonant. What's the probability of doing that? So the probability of our first event, choosing a consonant, we got 6 tiles and there are 4 consonants. So 4 out of 6 or 2 out of 3 is our probability of that. But next, what's our conditional probability? Given that we chose a consonant and did not put the tile back, what's the probability that we choose another consonant? Well, because we didn't put the tile back, again, we only have 5 tiles left in our bag. Out of those 5 tiles, because we chose a consonant first, how many consonants are left? Well, because we chose 1 out of the 4, there's only 3 left. So we have 3 out of the 5 tiles are consonants. Multiply our 2 individual probabilities. In this case, we could do 2 times 3 on top and 3 times 5 on the bottom, but we would reduce that. And so why don't we reduce first? We got multiplying by 3 and dividing by 3. Those operations just cancel each other. So we get 2 on top and 5 on the bottom, or approximately 40% chance. So slightly different odds of choosing 2 consonants in a row rather than a vowel followed by a consonant. Kind of interesting. One more example. This time we're going to go back to marbles. We have 3 white marbles and 2 blue marbles. And this time again we're not going to put the marble back after we choose the first one. So that would be these dependent events where one affects the other. Find the probability that you remove a white marble first, followed by a blue marble. Since we have 3 white and 2 blue, we have 5 total marbles in our bag. So our first event, sample size is 5. The chance that we draw a white marble, well, there's 3. So 3 out of 5 would be the probability of that event. But let's look at our condition now. Now that we drew a marble first and didn't put it back, we now have 4 marbles left. Out of those 4 marbles, how many would be blue? Well, because we chose a white marble first, we still have 2 blue marbles. So 2 out of 4, or 1/2, would be the probability of that conditional probability. Now we can just multiply our 2 individual probabilities. 3/5 times 1/2 is 3/10, or about 30% chance of drawing a white marble followed by a blue marble. So there's some examples of dependent probability. We started off with determining if it was independent or not, and then doing some independent probabilities. Either way, you are multiplying multiplying two events. In the case of dependence, you have to multiply the probability of your first event by the conditional probability of your second event. Given that they're independent, well, we just multiply the two individual probabilities, and hopefully that's enough for you to get going on your own.